Hey, this is Wonder. We're going to look at a couple of different oscillation circuits for AC circuits. The first one's called an LC circuit, and as you can imagine, it is just a capacitor and an inductor. So when I have a capacitor and it's connected to a resistor to form an RC circuit, that voltage across that capacitor decays very quickly, so it comes out very quickly. When it's connected to an inductor to form an LC circuit, the capacitor voltage undergoes some sinusoidal oscillation, so it actually does oscillate up and down. In the LC circuit, the discharge current from that capacitor has to pass through the inductor itself, which resists the changes in the current. So the current doesn't stop when the capacitor charge reaches zero. It does continue until it has recharged the capacitor with that opposite polarization. So this side might be positive and this one negative, and then when it flips, this will become positive and that'll become negative. And so as that repeats, the charge and the current do what we call oscillate. So this kind of go back and forth. So here we go. We've got, let's start right here. We have maximum current going through is like a block having maximum speed in an oscillator here. So I've got a block attached to a spring attached to the wall. So it's moving to the left and it's moving at maximum speed, but there's no compression yet at all. The current continues until the capacitor is fully recharged with the polarization that you see here. So that means that the block would be scrunched all the way up. So we have negative on the top, positive on the bottom plate. The discharge goes in the opposite direction. So now we've got the block moving the opposite way, which now means we have current flowing in the opposite direction. The current continues until the natural capacitor charge is restored. So then the capacitor charges up with the positive on the top, negative on the bottom. Capacitor discharges until it reaches a maximum. At that point, the cycle goes through again. So hopefully you can see kind of what happens both on the capacitor and through that inductor with that magnetic field. That oscillatory nature of an LC circuit is very comparable or comparable to what we would see for the mass on a spring, like we kind of looked at in that previous slide. So we're thinking about this horizontal motion of the block as it's attached to the spring. So we actually push it over, similar to here, and let go, and it goes to the right, stops, then starts to go back to the left, compresses again, and the cycle just continues to repeat. So the oscillation of the mass on the spring is really frequency is equal to 1 over 2 pi times the square root of k over m. If it was period, then everything would be flipped. But here the frequency of an LC oscillator is determined by the inductance and the capacitance. So you'll notice it's very similar. It's 1 over 2 pi again, and then our square root is of the LC circuit itself. So that would be the inductance times the capacitance. So here's a good example. We have an LC circuit. It has a 10 microhenry inductor. So we know this is 10 times 10 to the negative sixth, and a 500, and then picofarad is negative 12th. So 500 times 10 to the negative 12th. They want to know what is the oscillator's frequency. So we're looking for F. So from our equation, there's our F. We're going to do 1 over 2 pi times the square root of the inductance times the capacitance, and we get 2.3 times 10 to the 6 hertz, which would be 2.3 megahertz. So that was our that was our answer. So the frequencies of oscillators are usually much higher than mechanical oscillators, so they're megahertz or even gigahertz. So if you think about your cell phone, it does operate on a gigahertz frequency. So that's 10 to the ninth, and that's because of the LC oscillator on the inside. In the top circuit, we have an oscillation frequency of 1,000 hertz. They want to know what is the frequency of the one on the bottom. So all we've done here is we've added another capacitor. When we do that, we know that the angular frequency here is equal to the square root of 1 over LC. Series capacitors have an equivalent capacitance of C over 2, so I have 1 over, and then we can just make this 1, and we can do C over 2, and if you do that, we'll end up with 1410 hertz is what you end up with. RLC circuits are a little different. These have a resistor along with the inductor and the capacitor. And once the oscillations of an ideal LC circuit begin, they will continue forever, but all real circuits do have some sort of resistance in it. And that causes the amplitude of the voltage and the currents to decay. And what does that mean? That means that the amplitude, so going up and down, of that voltage will end up doing this. It'll end up decaying into nothing. And that decay can be modeled by adding a series resistor right here to that LC circuit. So I think there's going to be a similar picture here in a little while. In that RLC circuit, this circuit still oscillates, but the peak values of voltage and current do decrease with time. So this is really analogous to what we call a damped harmonic oscillator. Just like in real life, if I had a mass hanging on a spring, it loses energy over time and it stops oscillating as it goes. So here's a good picture of what that looks like. This would be in just a regular circuit. We've got the current in the circuit. Here's the maximum and the minimum, and you'll notice that over time it does decrease. This one has a 3 ohm resistance. The next one has a 6 ohm resistance, and because that resistance is bigger, we get a more rapid decrease in that oscillation. So both of these are damped. The bigger the resistance, so here's our bigger resistance, the quicker that dampness happens or damped oscillation occurs. To keep the circuit oscillating, we're going to add our good friend, that AC EMF source, and this makes what we call a driven RLC circuit. Because the reactances of the capacitor and the inductor, so we have reactances, remember, in these two, we have resistance in this, the current in this circuit varies with the frequency as well. So because of these things varying with the frequency, the current also will vary with the frequency on the inside. If the AC source frequency is too big or too small, the capacitor or the inductor's reactance grows very large, and as a result your current will just go to zero. So there's a resonance frequency where that current I is at a maximum, and the condition for resonance means that the reactance of the capacitor should be equal to the reactance of the inductor, and we had defined each one as 1 over 2 pi f. The original frequency times that capacitance is equal to 2 pi times the original frequency of the inductor times the inductance of the inductor. So if I want to solve for resonance, I would just combine my two equations and I end up with this. So here I have the frequency, that's the resonant frequency, where the two reactances are equal, is equal to 1 over 2 pi times the square root of L times C. So here it says if the value of my resistance is increased, the resonant frequency of the circuit, does it increase, decrease, or stay the same? And here it stays the same. The resonance frequency depends on C and L, but it does not depend on R. So if I increase R, that won't do anything to the resonant frequency because we're only worried about L and C. Kind of a trick question there. The resonant frequency of this circuit is 1,000 hertz. To change the resonant frequency to 2,000 hertz, we replace the capacitor with one having a capacitance of, and then this one is C over 4. So here, there's our resonant frequency again, and that's equal to 1 over the square root of L times C. So if I divide this by 4, it will double the frequency itself. So that's our frequency. The maximum current at the resonant frequency in this RLC circuit is determined using the magnitude of the EMF and the resistance, and so that driven RLC circuit is analogous to the driven damped harmonic oscillator. This is a good graph. It shows you as my resistance lessens, so as if it's really big here, I don't get as much current. As my resistance gets smaller, I do get a much bigger current. So at low frequencies, that capacitive resistance is large and the current is small. At high frequencies, the inductive resistance is large and the current is small. And at resonance, the current is limited only by the resistance. So you'll see that's what we want. We want those two reactances to be the same. The peak current then, so this is the equation. Don't let this equation freak you out. It's not that bad. This is the EMF. Here's our resistance, and then these are our reactances. So the reactance for the inductor and then the reactance for the capacitor. So you're basically just going to plug and chug in order to get that peak current. They want to know, it says, what is the battery current immediately after the switch is closed? So if I have this circuit, it does have a resistor, it has a battery source, and it has an inductor. When I close it, it should be 0 amps. It's because I haven't generated any current once I plug it in, because I have to wait for this thing to start working. After a very long time, they want to know what is the battery current, and this one would be 2 amps, because after a long time, then we don't worry about, we just know that the current here is going to be the same as the current in the resistor. Current in the resistor, remember, I is equal to V over R. Our voltage potential here is 10, and our resistance is 5, and so that gives us 2 amps. All right, so let's go ahead and take a look at the next thing. We're going to design a radio receiver. So an AM radio antenna picks up 1,000 kilohertz signal with a peak voltage of 5 millivolts. The tuning circuit has an inductor and a capacitor. So here's our inductor of 50 microhenries, and we have a capacitor that we can tune up and down. The inductor coil has a resistance of 0.25 ohms, and the resistance of the rest of the circuit we don't worry about. So they have 3 things. They want to know to what value should the capacitor be tuned to listen to the radio station. So when you, in old radios, you used to actually turn a dial. And when you did that, you were changing the capacitance of a capacitor. It was kind of a cool thing. Now everything's digital, so it works a little bit differently. But same thing happens when you press the seek button and it goes through, it changes the capacitance in the radio, but it does it automatically, which is really nice. They want to know what is the peak current through the circuit at resonance, and then a stronger radio station at 1050 kilohertz produces a 10 millivolt antenna signal. What is the current at this frequency if it's tuned to 1000? So in order to get ready for this, we know that the inductor's 0.25 ohm resistance can be modeled as resistance in series. So now we have an RLC circuit. The antenna has a frequency of 1000 kilohertz, where kilohertz is 10 to the 6 hertz, and that's the EMF. The circuit looks like that of 26.26. So we're going to back up to that 26.26. Here we go. Oops. It really kind of looks like this, essentially, is what you could say. So let's go ahead and take a look at this. The capacitor needs to be tuned so that the resonant frequency is 1000 kilohertz. So we know that that frequency is 1 over 2 pi times the square root of LC. We can solve for capacitance, which is C. So we basically go through and we need to solve for C here. So we've got to square both sides, then go ahead and do our substitutions. Once we do that, we get capacitance as 1 over L times the quantity 2 pi F, the original frequency squared. So here is our inductance. Here is our 2 times pi times that 10 to the 6 hertz squared, and we end up with 4.22 times 10 negative 10th farads, or 420 picofarads is what you would end up with. At resonance, we know that the reactance of the inductor is equal to the capacitive reactance. So the minimum current is going to be, the maximum current is going to be our potential over our resistance. And so that's just 20 milliamps or 0.02 amps. And then the last thing here is this 1050 kilohertz signal is off resonance. So the reactances are not equal. We know that the reactance of the inductor is going to be 396 ohms, and of that of the resistor, of the capacitor is going to be 359 at 1050. So the peak voltage of this signal is going to be 10 millivolts. With those values, we're going to use that bigger equation, plug everything in. So EMF, 10 millivolts. Our resistance is what we had earlier, and then we have XL and XC. Plug everything in, you should get 0.27 milliamps, and that is letter C. These are really realistic values to input for an AM radio. The signal from that 1050 kilohertz station is strongly suppressed when the radio is tuned to the 1000 kilohertz. So that's why you can hear the selected station, but not any of the other stations, which is a good thing. The rest of this really just goes through and summarizes the important concepts. So we looked at those AC circuits, we looked at what the wave looks like, and we talked about the equation a little bit. We looked at each one of the graphs, and we saw that the current here leads the voltage, and then the inductor, the current lags the voltage by a quarter wave. We talked about power and how we can use root mean square in order to find the root mean square voltage and the current itself. We talked about electrical safety. We've already talked about transformers before, so you don't have to worry about that. And then we did finish up with LC and LRC circuits. And that is the end of AC circuits.